Good morning. Today we're going to look at section 7.3, basic antidifferentiation. We're going to use the second version of the fundamental theorem of calculus. That came from last section, where we looked at the two versions of the fundamental theorem of calculus. These are things that should be memorized and known well. One of the versions of the fundamental theorem of calculus says that if we define an area function as the area underneath a curve, then the derivative of the area function will be the function we started with. The other version of the fundamental theorem of calculus says that if we start with a nice function, a continuous function on some interval, and we have any antiderivative, then we can use that antiderivative to evaluate the function. We're going to use that in evaluating definite integrals. And so what we'd like to do is, there's the tricky part that says, and someone miraculously gives you an antiderivative, we'd like to be able to produce the antiderivative. That's what we're doing in section 7.3. If I walk through it, our process is going to be to use the second fundamental theorem of calculus. And this is literally where you need to know your differentiation formulas backwards and forwards, because we're going to take differentiation formulas and do them backwards. So we'll start with the power rule for derivatives. The derivative of x to the n is n times x to the minus 1. We're going to integrate both sides of that and get the integral. Now we'll use the first version of the fundamental theorem of calculus, which says the derivative of the integral, or the integral of the derivative, gets me back to where I started with plus c. And here we have, so x to the n plus c is an antiderivative of n times x to the n minus 1 dx. I'm going to divide both sides by n, and I notice that c is an arbitrary constant, so this really should be c over n, but c over n is just a different constant. I'm now going to switch sides because I like to have my formula tell me what the antiderivative is. And everywhere I see an n, I'm going to replace that n by n plus 1. So x to the n plus 1 minus 1 is x to the n. X to the n plus 1, x to the n plus 1. This gives me my antidifferentiation formula. The antiderivative of x to the n is x to the n plus 1 over n plus 1 plus an arbitrary constant. Obviously, this formula doesn't work if n plus 1 is 0, because we can't divide by 0. So this is the antiderivative of x to the n, assuming n isn't equal to minus 1. Well, I can do that same process and get the other basic antidifferentiation formulas. And these are formulas that you need to have memorized, that you need to be able to quote out without any difficulty. So if we had a differentiation formula, which was the power rule, that gives us the antidifferentiation power rule. The derivative of ln of x is 1 over x. This was the missing case when n was minus 1. So the antiderivative of 1 over x is ln of x plus c. The derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x plus c. The derivative of a to the x is a to the x times ln of x. When I put my integral signs down, I'm going to have a to the x, and I want to divide both sides by ln of a. So the antiderivative of a to the x is going to be a to the x over ln of a plus c. Then we have some formulas on how do you build things together, and those formulas tell us something like the derivative of a constant times a function is a constant times the derivative of the function. So the antiderivative of a constant times a function is a constant times the antiderivative of the function. The derivative of a sum of two functions is the sum of the two derivatives. So the antiderivative of the sum of two functions is the sum of the two derivatives. And similarly, there is a rule for the difference of functions. Noticeably missing from this list there's no product or quotient rule. And I need an exact match to the first part of the formula to use a rule. And so we'll need more advanced techniques if we're given a function like x plus 2 cubed, because I wasn't given any formula that said x plus a to a power, only x to a power. Or the principal is 1,000 times 3% interest in however long it was since 2020. Off the top, I'm only told how to do it if this exponent is x, not x minus 2020. We're going to get to both of those cases in the next section when we do substitution. U substitution will be the equivalent of the composition rule, but there isn't a product or quotient rule, or those are things that we don't get to in this course. It's worthwhile now to look at some examples, and I'm going to look at examples that are out of the exercises. And so I'll start with just exercise 1 and then go to exercise 3. Exercise 1, because it's a nice simple one, it looks at f of x is equal to 3x plus 5. Well, then capital F of x is going to be 3. X goes from the first power to the second power. I divide by 2, plus 5 times x plus a constant, and we don't care what the constant is. And so what I'm using at the heart of it is I'm using the power rule in those cases, have the power of x times a constant, and I've added them together, so I've really used 3 rules. If I wanted to do all of the steps, I would say the antiderivative of 3x plus 5 dx is the antiderivative of 3x dx plus the antiderivative of 5 dx, which is the antiderivative of 3 times the antiderivative of x dx, plus 5 the antiderivative of 1 dx, and this will become 3x squared over 2. I'm going to say plus c1 plus 5x plus c2. We're then going to go to exercise 3, which is the same idea, just with silly numbers in it. And so for exercise 3, I'm looking at f of x is equal to x to the 3,124,567 plus 2 times x to the 473 plus 327 times x to the minus 2,786,534. Sometimes rules are easiest to understand if you work with silly examples. So the antiderivative of this is going to be x to the 3,124,560, 7 plus 1 is 8, divided by 3,124,568, plus 2 times x to the 44 divided by 44, plus 327 x to the minus 2,786,533, because when you add to a negative number, it goes down, divided by minus 2,786,533. And so those are two problems that show us we now have enough to do polynomials and pseudo-polynomials. I want to go a little further down the page and look at what would be problem 5. I'm interested in the case where f of x is equal to e to the x plus 1/2 to the x. F prime, its antiderivative. Well, the antiderivative of e to the x is just e to the x. The antiderivative, we have 1/2, the antiderivative, and I need to write this properly. The problem was 1/2 raised to the power x. So I'm going to have 1/2 to the power x divided by the ln of 1/2. I think it's important in this class that we learn about bases other than e, because the kind of bases you're most likely to see something that looks like 1.03 to the x, because that will be used in interest and compound interest and growth. So that gives us enough of the problems that are simple, find the antiderivative. In the next segment, we'll look at some more complicated exercises for this section. Thank you.